So this is the big picture of how the code architecture should move from what it is currently to what it will be. So right now, it's pretty much a siloed monolith, although it has been broken down a little bit since then. We've already made some improvements, or the teams have already made some improvements. So, right now we have pretty much a siloed monolith that's been broken down a little bit. And we're going to be moving to a modern web application. And the next few slides will look at what that means. So how do we move from a siloed model to the modern architecture of a web application? So one of the big things in this particular case, with the multi-tenancy being so important, is to introduce tenancy early. So we have already done some of that, but we haven't got all the way yet. So looking at things like how a tenant registers as a new tenant, how we manage a tenant, how we bill a tenant, what the isolation policies are, looking at onboarding, those kind of things. So that's stuff that we've been doing that already, but there's a lot more to do, and we're partway through that. So as I said, we've done some of the work towards moving from where we are now to the future already. So in this case, we've already moved to the place where we have a tenant per VPC in IG. So for example, OMAS has its own VPC and StackC has its own VPC in IG. That is kind of the first step away from the monolithic siloed tenancy kind of thing, and that's where we've moved to. So the first step is moving into a VPC like that. So onboarding and tenant provisioning would come before the creation of that tenant. And in the first step, that tenant would be created manually. And that is kind of almost where we are now, although we've moved a little bit further to the next slide. So the next stage is to automate the provision of tenant silos. So create the VPCs automatically, create the database and the EC2 instances within the VPC, and maybe the Kubernetes and so on within that automatically. And IG is well on the way to doing that. It's very close to being there already, but it's not quite there. So we've done that part. So now the aim is to get tenant provisioning, completely automated. So this part we already have in place. We inject some tenant context into the whole scenario as the user gets authenticated. We do this in advanced authentication. So that part already exists, and the logged in person then, or customer, then takes that identity with them into IG with some context information. So AA does this part up front, injecting that context so that we know something about the customer. However, or the user, I should say. So the user context information will grow over time. That's what's expected. So the next stage typically is to go towards, managed monoliths. So we would prefer to have some kind of tenant management, user management, registration, and identity in kind of a shared services environment. This is kind of our customer portal to some extent, and maybe we'll go towards more of the customer portal as it is, or maybe some of the customer portal features will be integrated into the other products. I'm not sure, but typically other companies that do this kind of thing, they keep it separated out as a shared service, and it would stay as customer portal basically. So AA and IG would use some of this tenant management and user management stuff, but it will be sort of managed within a shared services environment, which is basically customer portal. So in a typical environment where we're going towards the modern kind of web application, as we go along, we're going to find microservices that are common to many tenants. And the microservice, if you don't know what a microservice is, it's a very small piece of functionality that is in charge of a very small piece of data. And it can be called from any, in this case, from any tenant, but from any application and from any web application. Usually it's exposed via some sort of API, normally a REST API, get, post, put, patch, delete. So that's what a microservice is. And normally at some point along the line here, there'll be some identification of some key functionality that could easily fit into a microservice. That there's some components that need to be in place for a microservice. For example, a microservice must be stateless, and it must be, kind of small and only own a small amount of data and so on. And the reason for that is because one of the benefits of microservices is that you can scale up and scale out a single microservice without affecting any of the other microservices. So when you're designing microservices, you have to think about that. Can I scale up only this microservice when something happens? And if you can, then it's probably a good microservice boundary. So just some tips on how to choose a microservice in your architecture. Normally, you would choose one that has very limited coupling for the reason that I just said before, so that you can scale up and scale out without affecting other microservices. So if this particular piece of functionality can be scaled up without having to scale up other microservices as well, then it's probably a good boundary. Minimal impact on business continuity. You don't want a microservice to fall over all the time. You don't want it to be a critical microservice when you're first starting out, when you're first creating microservices. When you first start microservices, you want to start very small, and you want to start with something that it's not critical if it doesn't work properly. For example, I think in IG, they have a tenant creation Lambda microservice, which it just sets up a tenant. Now, if that doesn't work, you can just go back and do it manually, so that's fine. So that microservice doesn't depend on anything else, really, doesn't interact, doesn't couple with anything else. And if it stopped working tomorrow, we could still carry on with just do it manually instead of doing it automatically. It doesn't make a huge impact. And then another good use of microservices, or starting off with microservices, is to target tenant bottlenecks. So if there's a particular piece of code that is really slow or is causing problems in a particular tenant, or even in multiple tenants, it might be a good idea to separate that code out into a microservice so that you can scale it up or scale it out as needed, so that if lots of tenants suddenly hit it all at once, it can scale up and handle the extra load, and then scale back down when there's fewer tenants accessing it. So one of the steps that we recommend for the code architecture is to containerize the code where possible, especially if it's a microservices already. Then containers are really good for that. Think of a container as a bit like a shipping container in the real world that you have on the back of a truck, or you can send by a train, or you can ship on a ship across the ocean, and so on. Containers are just like that. They can be shipped anywhere. The idea behind a container is that it's more secure because nothing can get in and nothing can get out. And that's true of the shipping containers as well as the containers we're talking about in the coding world. Nothing can get in, nothing can get out, so it's kind of secure the way, assuming it's been built correctly. We can transport it easily. So when we're talking about code containers, we package all the code together. No changes will be made internally to that code before it's run on some other platform or some other machine. and it transports very easily. You just download it or copy it from an orchestration system and so on. It contains anything, so just like a shipping container in the real world, you can put just about anything into a container in the computing world. So with a shipping container, you would send maybe a piano and maybe some paintings and maybe a car and things like that. In the computing world, a computer can contain Java, C#, Go, Python. It can contain big applications, small applications. It can contain more than one application, more than one website. It can contain APIs and so on. And there's no bleed or spillover in these cases. The idea is that the container cannot affect any of the other containers in the same environment. So just like a shipping container, hopefully nothing will ever leak out of there and end up affecting anything in another container. The same thing with a container in the computing world. The memory and CPU and so on like that is internal to it and cannot affect the other containers running in the same environment. So eventually you get to a situation where the tenant coming in is routed to an application or a web service or a microservice, depending on the functionality that they want to access, and gradually it all moves further and further towards microservices servicing everything. And that's the ultimate nirvana that we're aiming for here. So one thing that has been noticed in a microservices architecture is that each microservice handles a very small piece of work, and sometimes you need to kind of aggregate and collect from multiple microservices data before returning it to the client or the customer. And in many cases that has been for reporting or anything that aggregates information, printing, that kind of thing. So there are different ways of handling that. In Lambda's case, so if you have a Lambda microservice, for example, in this case it would be a Lambda function which serves as a microservice. The function might have access to layers. Now, layers are kind of common functionality that can either aggregate or work across many microservices. So in this case, it would be the microservices are implemented as Lambdas, and the common functionality that is needed to work across all of those Lambdas is stored in layers. And a JWT or JWT token would give the context. So it would basically say, this is the customer that's logged in, this is what they have access to, which normally it's API routes and which methods they're allowed to. So if they're allowed to do a get, a post, a put, a delete on a particular API endpoint, that kind of thing, which endpoints they're allowed to access and that kind of thing. And that JWT token will be passed between the Lambda and the layers to indicate, what permissions they have, that kind of thing, and what context that information is used in.